So previously we were introduced to this random number generator that's built into GlowScript that creates a random number between 0 and 1. And we saw how you can transform it into a random number generator between any two numbers that you like using this little setup here in this function. And these can be integers, these can be floating point numbers, they can even be in reverse order, and this random number generator works. I gave the caveat that this is a uniform probability random number generator, meaning you're equally likely to get numbers from anywhere in this range. That's not always the way random numbers work. So, for example, the most common random number distribution is the normal distribution. That's the one where you've got the two tails going off to 0, and then you've got a peak at the middle, and you've got a nice, well-defined standard deviation. There is a way to take your random number, or your uniform random number generator, and turn it into a normal distribution, and that's using the Box-Muller transform. I'll place a link to that in the description below. But basically what you do, if you want to create a normal distribution, you can set up a function. Let's call it normal, since it's a normal distribution. A normal distribution is described by its average and its standard deviation. So we'll use AVG and St. Dev for those. What you do is you get two random numbers between 0 and 1. So we'll call them U1 and U2. And I'm storing those random numbers here so that I can access them later. But basically you get two random numbers and you apply this little formula here. Let's call it R for random. You take the square root of -2 times the natural log of the first one, or it could be the second one, doesn't really matter because they're random, times the cosine of 2 times pi times the second one, or again, it could be the first one. Either way, you put one in the natural log and one in the cosine. And basically what you're doing here is you're transforming this uniform distribution onto a normal distribution. So that's where the log comes from, is from undoing the exponential. The cosine comes from taking these things in the xy plane and just transforming them into polar coordinates. At least that's my understanding based on what I've read. Either way, this is the thing that works. So I'll leave the article in the description below so that you can read about where it comes from. But what you notice is we haven't yet incorporated the average and the standard deviation. So what this transform by itself does is returns to you a uniform distribution with an average of 1 and a standard deviation of 1. So this one gives a normal distribution with average and standard deviation equal to 1. Standard deviation, there we go. But you can easily transform that into whatever average and standard deviation you want. The standard deviation is the width of the distribution. So to get that, you can change R into R times standard deviation. And then the average just shifts the location of the peak. So you can just add the average. So this will change your unit distribution, as it's called in the article, with the average equal to AVG and standard deviation equal to St. Dev. So then you can just use return R and you'll have your normal distribution. Let's test that out. So let's make a print of normal with an average of 5, and let's give it a small standard deviation. Let's give it a standard deviation of 0.01, meaning we're most likely to get a number pretty close to 5, since we have such a small standard deviation. And lo and behold, we do 5.01, so we're almost exactly 1 standard deviation away. And you can repeat this over and over again, like we've seen before. You'll get a different number every time. If I keep doing this one, I'm going to get numbers that are close to 5. If I make my standard deviation broader, so say we make it 1, I'll get numbers that are farther away from 5. So 4.66, 6.1, so that's more than 1 standard deviation away. 5.9, again, you still get ones that are pretty close, again, because it's peaked around 5. But if I make this very broad, so say I make this 10, I've got a very broad distribution, so I can get numbers that are very far away from the average. Now, of course, that's all nice to look at, but the question is, am I actually getting that average, and am I actually getting that standard deviation? Well, we can test that. If we generate a whole bunch of random numbers and take their average, we can tell whether we get the appropriate average. So let's set up a for loop to generate the numbers for us. So let's say for I in range, and let's get 100 values. That should be able to, that should get us a nice zoom in on the average. Let's see here. So I want to generate kind of a random value. So let's call it val. And let's make it normal. And let's make the average, let's go with an easy. Let's make the average 0 and the standard deviation 1. So you've got a whole bunch of positive and negative numbers, mostly within plus or minus 1, and they should be canceling out. Okay, so if I just do this, it's going to, it's going to give me a bunch of random variables, but it's not, a bunch of random numbers, excuse me, but it's not going to do anything with them. So I need to start with an average. So let's make the sum. So the average is the sum divided by the number that you generate. So let's go with sum equals sum plus value. And then after I leave the loop, I can take the average as the sum divided by the number. So I've got 100 of them, so we'll divide by 100. And then we'll print the average. And now we're hoping that we get an average of 0. Actually, let's label this thing average equals. It's always nice to put text next to your number so that you know what it is that you're printing, especially since we got a bunch of stuff left over from last time up here. So let's run this. We should be getting an average of about 0. And that's pretty close to 0, right? I mean, that's 0 out to one decimal place. It's 0.01 if you really wanted to round, or 0.008 if you wanted to round a little bit more, a little bit farther out. And of course, the greater number of random numbers that I generate, the closer that's going to be to the average. Of course it's not. And of course it's not going to work the one time I say that. That's odd. Oh, right, because I need to divide by 1,000. All right, here we go. Let's do this. Let's go with number equals 1,000. We'll go from 0 to number. I forgot to update the thing I was dividing by, so let's do the smart thing and make it a variable, so we only have to change it once. There we go. Now we're getting better off. Let's turn this to 10,000. Let's do it one more time to see. Yeah, we're good. I think we're just well off doing 100. There we go. Let's see here, and we're getting a nice decimal for that. Of course, so my average is coming out to pretty close to 0. Let's actually make this a little bit easier to recognize. Let's make this an average of 1 with a standard deviation of 0.1. Okay, yeah, I recognize that as being close to 1. It's kind of hard to tell when something is close to 0 because technically every number is infinitely far away from 0. So let's try that out. There we go. Now, of course, I promised you that it has this average and this standard deviation. There's a way to get the standard deviation, and that's to take the average of the squares minus the square of the averages. Let me give you an idea of what that means. So I need another sum. I need sum of squares equal to 0. And basically what you're doing there is you're taking sum of squares and you're adding up all the values each individually squared. So this is the first number squared plus the second number squared plus the third number squared plus the fourth number squared, etc. And you can make the average of the squares by taking the sum of the squares and doing the same thing. You divide by the number. Yes, just checking my notes to make sure I did that correctly. I sometimes mess up standard deviation. So the standard deviation then is just the square root of the average of the squares minus the square of the average. So I take the average and square that. So average of squares and square of the average are not the same operation. Those two operations do not commute with each other, right? Because once you it's a difference of whether you're squaring and then adding or adding and then squaring. Those things have different locations in the order of operations. So those are different. So I can print another thing to tell me the standard deviation equal to standard deviation. And so now I should get an average of 1 and a standard deviation of about 0.1. The average is usually a little bit more reliable than the standard deviation, but let's find out. All right, lo and behold, I get an average of just shy of 1. I mean, it's 0.002 away from being 1. And this thing is pretty close to 0.1. It's 0.004 away from being 0.1. So we're doing pretty well there. Of course, if I make this larger, let's see what happens there. Yeah, this thing is a little bit farther from 1 because we've got a larger standard deviation, so it's not quite as reliable. But our standard deviation comes up pretty well, so I'm pretty impressed with that. So there you have it, a nice, simple way of getting a normal distribution out from your regular uniform distribution between 0 and 1. So I hope you have some fun with that for when you need some normal probability distributions. Thank you so much for watching. I will see you next time. Bye-bye.